let y is equal to f of x be a continuous function defined on a closed interval a comma b. Assume that all the values taken by this function are positive, so that the graph of the function is the curve above the x-axis. The area bounded by the curve y is equal to f of x. The ordinates x is equal to a, x is equal to b, and the x-axis is given by the definite integral shown here. Now, let's see how to approximate this area. Consider region ABDCA. Let the area of this whole region be denoted by t with subscript a. Divide the closed interval a comma b into some small sub-intervals, each of the same width. Now, choose the least value of f of x in each sub-interval and construct rectangles as shown here. The sum of the areas of the rectangles whose area is less than the total area bounded by the curve is called the lower sum. Next, choose the greatest value of f of x in each sub-interval and construct rectangles with that as its height as shown here. The sum of the areas of the rectangles whose area is greater than the total area bounded by the curve is called the upper sum. In this way, we have sandwiched the area that we have to find between the lower sum and the upper sum. The larger the number of rectangles we draw, the smaller will be the difference between the upper and the lower sums. So finally, the better approximation of the area under the given curve can be calculated. This approximation will be equal to the limit of either the upper sum or the lower sum. Based on this discussion, we conclude that the difference between the upper and the lower sums approaches zero as the number of rectangles in the area subdivided approaches infinity. The area under the curve is equal to the limit of either the upper sum or the lower sum as the number of subdivisions tends to infinity. The area under the curve is represented as the limit of a sum. We shall now introduce notation to understand this concept more precisely. Consider a closed interval a comma b. Divide it into n equal sub-intervals, each of width h denoted by closed intervals x0, comma x1, x1, comma x2, and so on up to x r minus 1, comma x r, and so on till x n minus 1, comma x n. Here x0 is equal to a, x1 is equal to a plus h, x2 is equal to a plus h, which is equal to a plus 2h, and so on till xr is equal to a plus rh, and xn is equal to b, which is equal to a plus nh. In other words, n is equal to b minus a divided by h. As n tends to infinity, b minus a divided by h tends to infinity. This implies h tends to 0. Therefore, region ABDCA under consideration is the sum of n subregions, where each subregion is defined on a closed subinterval. From the diagram, it can be understood that the area of the region containing the lower rectangles is less than the area of region ABDCA, which in turn is less than the area of the region containing the upper rectangles. Now, let's find out the sum of the areas of the lower rectangles. Let the sum of the areas of the lower rectangles or the lower sum be denoted by L with subscript n. Therefore, Ln is equal to f of x naught into h plus f of x1 into h plus and so on plus f of x r minus 1 into h plus and so on up to f of x n minus 1 into h. So the lower sum is equal to the summation of f of x r into h, where r is a running from 0 to n minus 1. Let's denote this as equation 1. Next, let u with subscript n denote the sum of the areas of the upper rectangles or the upper sum. So the upper sum, u with subscript n, is equal to the summation of f of xr into h, where r is running from 1 to n. Let's take this as equation 2. Recall that we have denoted the total area bounded under the curve by t with subscript a. Hence we have the lower sum less than or equal to TA, the total area of which is further less than or equal to the upper sum. Symbolically, this can be written as shown here using the equations 1 and 2 above. As n tends to infinity, the rectangles become narrower and narrower. It is assumed that the limiting values of the lower sum and the upper sum are the same in both the cases, and that the common limiting value is the required area of the curve. Therefore, the area is equal to the limit of the lower sum or the upper sum as the number of subdivisions tends to infinity. It can be written as shown. So this limit of a sum as the width of each subinterval approaches 0 and the number of subintervals approaches infinity is called the definite integral. Mathematically, this area can be denoted as integral of f of x dx from a to b. So the integral follows that the required area is the limiting value of the lower sum or the upper sum. Thus, the integral of f of x dx from a to b can be expressed as the limit of the sum, which is given as shown here. This can also be expressed as shown. Here h is equal to b minus a divided by n as n tends to infinity. The value of the definite integral given in a particular interval does not depend on the variable of the integration that we choose, but depends on the function and the interval. That is, integral of f of x dx from a to b is equal to integral f of t dt from a to b is equal to integral f of u into du from a to b. This variable of the integration is called a dummy variable.